In this video, we're going to talk about designing experiments. At this point, we know a little bit about experiments and that they are the preferred method for examining the effect of one variable on another, right? Cause and effect, that's what we're looking for most of the time. And I'm sure that you've done experiments in your science classes, for example. And so those are mostly lab experiments, and those are a lot more controlled than those out in the wild. But many lab experiments use a design like this. They have experimental units. Who are they testing on? What are they testing? And treatment, again, what are they testing? And any kind of manipulation that they're going to throw in there, whatever the treatment is. And then, of course, they measure the response. Does this cause have an effect? But outside of a lab, experiments are often conducted with animals and people, for example. And we often use two groups because there are a lot of variables that can affect an experiment on animals and people, for example. So those two groups are an experimental group. So those are the ones that get the treatment. They get the supplement, for example. They drink the caffeine. And then there's a control group, and those don't receive the actual treatment, but they don't know that they haven't received that actual treatment. So in an experiment, a control group is used to provide a baseline for comparing the effects of other treatments. So depending on the purpose of that experiment, a control group may be given an inactive treatment, a placebo, an active treatment, or no treatment at all. So both groups should be treated exactly the same to measure any convincing evidence of an effective treatment. This video is going to be chock full of examples, and here's our first one. Remember preventing malaria in those 101 Kenyan schools? Well, let's talk about them yet again in terms of a control group. So, the problem, again, in that example, we described an experiment in which researchers randomly assigned 101 schools in Kenya to either receive regular screenings and follow-up treatments or to receive no regular screenings to malaria. So explain why it was necessary to include a control group of schools that didn't receive regular screenings. So in this case, the purpose of a control group is to provide a baseline for comparing the effect of the regular screenings and the follow-up treatments. Otherwise, researchers wouldn't be able to determine if a decrease in malaria rates was due to the treatment or some other change that occurred during the experiment, like a drought that killed off mosquitoes, slowing the spread of malaria. So in this case, a control group was essential to determine if the screening and those follow-up treatments were effective. Not all experiments include a control group. As long as you have a lot of groups being treated and experimented on, technically, going on at the same time, like that 5-second rule experiment where there were many, many different things happening with the type of food, the type of floor, how long you waited, the kind of preparation of the bacteria, all that good stuff. So if you are just comparing, hey, is this thing effective or not, you definitely need a control group, like in this malaria example. Something that comes along with control groups and placebos is something that we call the placebo effect. And that describes the fact that some subjects in an experiment will respond favorably to any treatment, even an inactive one. So it's important that your subjects don't know which treatment they are receiving due to this effect, because obviously it will influence your experiment. And if you can make it work, it's also important that those working with the experiment subjects don't know which treatment the subjects are receiving. So that brings us to the two types of experiments, or what we call the two different kinds in terms of the placebo effect. So the first is double blind. That's where nobody, except for your statistician, of course, somebody should know what's going on, but the people receiving the treatments and those that are working with those receiving the treatments, they don't know what treatment the groups are getting. And then there's single blind, where either the subjects don't know which treatment they're getting or the people that work with them don't know which treatment they're getting, one or the other. Ideally, the subjects just shouldn't know what they're receiving, but sometimes that's hard to avoid. Either way, your experiment should be double blind or single blind because, well, the placebo effect. All right, let's put that into a lovely example. This one's called, Do Magnets Repel Pain? So, our problem is that early research showed that magnetic fields affected living tissue in humans. Some doctors have begun to use magnets to treat patients with chronic pain. Scientists wondered if this type of therapy really worked. I'm sure you do too. They designed a double blind experiment to find out. A total of 50 patients with chronic pain were recruited for the study. A doctor identified a painful site on each patient and asked him or her to rate the pain on a scale from 0, which is mild pain, to 10, which is severe pain. Then the doctor selected a sealed envelope containing a magnet at random from a box with a mixture of active and inactive magnets. I don't know what that means. Maybe you do. The chosen magnet was applied to the site of the pain for 45 minutes. After being treated, each patient was again asked to rate the level of pain from 0 to 10. So let's do two different things. Let's explain what it means for this experiment to be double-blind, and why was it important for the experiment to be double-blind. So in this case, what it meant for the experiment to be double-blind was that neither the subjects nor the doctors applying the magnets and recording the pain readings knew which subjects had the active magnets and which had the inactive magnets. I still don't know what that means, but it must mean something. And now, why was it important for this experiment to be double-blind? Well, if subjects knew they were receiving an active treatment, researchers wouldn't know if any improvement was due to the magnets or to the expectation of feeling better, aka the placebo effect. And if the doctors knew which subjects received which treatments, they might treat one group differently than the other, which would obviously affect the experiment and the results. This would make it difficult to know if the magnets were the cause of any pain improvement. Beyond that, if treatments are given to groups that differ greatly when the experiment begins, confounding will result. And we know confounding is not what we want. So in order to create roughly equivalent groups at the beginning of an experiment, we use random assignment. Yet again, another place where randomness helps us or comes into play. So what is a random assignment? In an experiment, a random assignment means that experimental units are assigned to treatments using a chance process. So let's apply random assignments to caffeine and pulse rates. So let's say a total of 20 students have agreed to participate in an experiment comparing the effects of caffeinated cola and caffeine-free cola on pulse rates. So let's describe ways in which we would randomly assign 10 students to each of the two treatments, caffeine and caffeine-free. So one will be using 20 identical slips of paper and the other will be using technology. So using paper, you take half of those slips of paper, so 10 slips of paper, and write either the letter A or the number 1 or some other symbol, as long as it's all the same. And then on the remaining 10, you write something else, like the letter B or the number 2. Again, as long as it's all the same on those 10 slips. You shuffle the slips, you hand them out, or you have the students pick from a hat, whatever you want to do. Students who get an A or a 1 or whatever that one symbol is are in the group who receives caffeinated soda. And the students who get the other symbol, or the B or a 2, are in the group who receives caffeine-free soda, or vice versa. With technology, much like using an SRS or a random number generator, you're going to label each student with a different integer from 1 to 20, or some other 20 numbers. Then you randomly generate 10 different integers from 1 to 20 without replacement. And then those students selected get the caffeinated soda, and the rest get the caffeine-free soda. Along with randomly assigning different subjects to different groups, experimental and control groups, we have this idea of control. And that might mean a lot of different things to you. But in statistics, in an experiment, control means keeping other variables constant for all experimental units. So we can control the effects of some variables by keeping them the same for both groups. So taking into account that example that we just looked at with caffeinated and non-caffeinated soda and its effect on pulse rate, or its possible effect, some things that you can do is you can keep the amount of soda constant for each participant, or you can not keep it constant. You allow those subjects to drink as much or as little as they want. In that case, we might get a result like this, where there's caffeine that's measured and no caffeine that's measured between the two groups, and the difference in their pulse rate. So compare that, something that you didn't control, to something that you can control. So that is keeping the amount of soda constant and the effect on the pulse rate. So you're going to get different results for the number of things that you control for or don't control for. So once you have figured out what you want to study, what causes an effect, and you've randomly assigned your subjects or your experimental units into their groups, and you've controlled for all the possible variables that could be impacting your experiment and your treatments, there's one last thing you need to take into account, and that is replication. So in stats, in an experiment, replication means using enough experimental units, so those are people or animals or whatever it is that you are studying, to distinguish a difference in the effects of the treatment, so what you're doing to those animals or those people, from chance variation due to the random assignment, so those groups that you put them into. So replication in science, for example, could mean, can you replicate? Can you repeat this study over and over again? And in other branches of science, I'm sure replication has other meanings, but in statistics specifically, it means use enough subjects, use enough people, use enough animals or things. All right, again, putting all these things together, the principles of experimental design are as follows. First, that comparison. Use a design that compares two or more treatments. That random assignment. Use chance to assign experimental units to treatments. Control. Keep other variables the same for all groups, especially variables that are likely to affect the response variable. Helps prevent against confounding, or as much as you can prevent against it. And then, of course, replication. Use enough experimental units, use enough subjects, as people, animals, things, in each group so that any differences in the effects of the treatments can be distinguished from chance differences between the groups. We're going to look at one last example where we're going to analyze the principles of experimental design on something called the Physician's Health Study, which you may have heard of, or at least heard the results of. So the problem says, does regularly taking aspirin help protect people against heart attacks? The Physician's Health Study was a medical experiment that helped answer this question. In fact, the Physician's Health Study looked at the effects of two drugs, aspirin and beta-carotene. Researchers wondered if beta-carotene would help prevent some forms of cancer. The subjects in this experiment were about 22,000 male physicians. There were two explanatory variables, or factors, and each of them had two levels. Yes or no to aspirin, and yes or no to beta-carotene. Combinations of the levels of these factors form the four treatments shown in the diagram, which I'll show you on the next slide. 1/4 of the subjects were assigned at random to each of these treatments. So, on odd-numbered days, the subjects took either a tablet that contained aspirin or a placebo that looked and tasted like aspirin but didn't have any active ingredients. And then on even-numbered days, they took either a capsule containing beta-carotene or a placebo. There were several response variables. The study looked for heart attacks, several kinds of cancer, and other medical outcomes. After several years, 239 of the placebo group, but only 139 of the aspirin group had suffered heart attacks. This difference is large enough to give good evidence that taking aspirin does reduce heart attacks. It does not appear, however, that beta-carotene had any effect on preventing cancer. So as promised, here is our lovely diagram where the factor 1 was aspirin and the factor 2 was beta-carotene. And if they had both, yes and yes, they took both aspirin and beta-carotene, and then any other combo of yes and no, or no and no, would mean some combo of a placebo and the actual aspirin or beta-carotene, or both placebos. What fun. So the first thing that we're going to do is we're going to explain how this experiment used comparison, that first step in an experiment design. So remember, comparison is a design that compares two or more treatments. In this case, researchers used a design that compared each of the active treatments to a placebo. So they used comparison, most certainly. Next, let's explain the purpose of randomly assigning the physicians to the 4 treatments. So although we don't know how exactly they were randomly assigned to the group, random assignment does help ensure that the 4 groups of physicians were roughly equivalent at the beginning of the experiment. Next up, let's name 2 variables that were controlled in this experiment and why it was beneficial to control these variables. Remember, we use control to help avoid confounding and to reduce variability in the response variable and in the results of the experiment. So in this experiment, they use subjects of the same gender and the same occupation, and using only male physicians helps to reduce the variability in response variables. And last, let's explain how this experiment used replication, which is that 4th aspect of experimental design, and let's figure out what the purpose of replication is in this study's context. So remember that replication is about using enough subjects. And in this study, there were roughly 5,500 subjects, or male physicians, in each treatment group. So this helped ensure that the difference in heart attacks was due to aspirin and not to chance variation in their random assignment. All right, that's going to do it for this video. Thanks for watching.